Z3 here, just if I want to, this one, which is the Z3, we got the Z3 by multiplying the amplitude, so we have 12.851.34, 12.851, 34, 3.6 times 3.6, 133.7, 33.7 degrees divided by 13.6, 36. So we multiplied the magnitudes here. So Z3 was 12.8 times 3.61 divided by 13.6, and the angles here was 51.34. We added, so minus 33.7, and then we subtracted minus 36 degrees, there where we got Z3 to be 3.4 minus 18.36 degrees, right? And then we had that Z3 in series with minus J10. So we now, in order to add them, this is an imaginary number. In order to add them, we have to take the Z3 to the rectangular format. So we went to the rectangular format, and we got Z3 to be 3.23 minus J 1.07. Then we added to that imaginary, we got the Zn. Now, if you want to keep the Zn as a rectangular, or if you want to take it back to the polar, it's up to you. Unless you were uh, explicitly asked to find it in polar, then this is something else. Other than that, this should be sufficient. Any question about how did we calculate the total impedance? Okay, that's good. So let's move on then. We have more examples. Always remember that we said that our reference sinusoid is the cosine. So we have always to uh, transform all sinusoidal functions minus sine or sine into a positive cosine. So before I do this, I would like to remind you with the angles here, how to make or how to get a correct angle for a polar coming from the rectangular. So always remember that the complex plane here, the real and the imaginary, we have here four quadrants in polar. So let's assume I have a positive. So let me write this: z equals to x plus j y. This complex number in rectangular format, and I would like to transform it to the polar format. So in this case, we know that we can find the magnitude being x squared plus y squared. So you have always a positive magnitude. J does not go inside the magnitude. We only take the coefficient of the j. Only the coefficient of the j. We don't take the j inside. And then the angle, and this is what I want to talk about, is the tan inverse y over x. Now we have four cases here. The first case is when both the real and the imaginary are positive. And in this case, if the real is positive, let me do this in black color, and the y is also positive, do this in black, then you will definitely get a positive angle, and this angle will be in the first quadrant, right? So this one is the x squared plus y squared, and then this is theta, the one that we talked about here. So this is theta. Positive, positive, you're going to get theta in the first quadrant. Okay, so let's look at the other three cases here. And let me take different colors. Uh, the red, so if z equals to x is positive, however, the imaginary is negative. So in this case, x would be, uh, just a second. Okay, so we have now the x as positive, y as the imaginary as negative. So in this case, again, this is the x imaginary is negative here, and in this case, the the angle would be in the fourth quadrant, and would be minus theta. So you have to be careful. So far, things are straightforward. Imaginary positive will give you the angle right away as the correct angle. Imaginary negative will give you the tan inverse is going to give you a negative angle right away. That's not the tricky part. The tricky part are the other cases. So here, theta is tan inverse minus y over x, and you are gonna get a negative angle, so you don't need to do anything about it. But where is the tricky part? The tricky part is when you have the real part as negative. That's one of the tricky parts. So z equals to minus x plus jy. And in this case, theta would be tan inverse of y positive over minus x. But guess what? The old calculators are going to understand. They're not going to distinguish between minus y over x or y over minus x. It is going to give you a negative angle. But guess what? The correct angle is not in the fourth quadrant because this negative angle means fourth quadrant. So what you need to do, since I'll redraw this, and again here. So we have the real as negative, so I have minus x here, and I have the imaginary as positive y here. So the correct quadrant is the second quadrant. So this is the angle. But your calculation gave you minus. Your calculation gave you minus. Let's take an example. So to understand. So if I have z equals to minus 4 plus j2, then z equals to 4 squared, or you can say minus 4 squared, it doesn't matter, it's going to give you a positive anyway, plus 2 squared. And the angle is tan inverse of 2 divided by minus 4. So z here is square root of 4.47, and the angle is, if you plug in, and the old calculators, of course, the newer ones now can distinguish. So tan inverse of 2 divided by minus 4, your calculator is going to give you minus 26.56, but that's not the correct angle. So your calculator is going to give you minus 26.56, but this is not the correct angle. This is in the fourth quadrant. So what you do is you add 180 degrees to it. So this is wrong because this is in the fourth quadrant and you're expecting your angle to be in the second quadrant. So what you do is you add 180 degrees to it, minus 26.56. And in this case, the correct angle would be 153. 153.4 degrees. So this is the correct angle. The same thing for when both of them are negative. So when both of them are negative, and in this case, z equals to, let me take an example right away, minus 5 minus j3. So in this case, the real is minus 5, and the imaginary is minus 3. So in this case, you're expecting the angle to be in the third quadrant. And we always take it the closest to the real axis. So since it's closer to the real axis from the lower part, so we take it as minus, and you will see what do I mean by that. So this is the correct angle. Now, if you transform this, so you have here minus 5 plus minus 3, so the minus is not going to do anything. Tan inverse minus 3 over minus 5. And if you plug those numbers in your calculator, you're going to get a positive angle, which is wrong. So square root, take the square root of 25 plus 9. So this is z equals to 5.83. And the angle here, based on plugging minus 3 divided by minus 5, it's going to be 30.96, which is wrong because this is in the first quadrant and I'm expecting my angle to be in the second, in the third quadrant. So what's the solution? What do I do here? Minus 180 degrees. Minus 180 degrees because it will be read from this direction. being closer to the real axis is looking at it from the negative side, which basically, so this is what we got. This is the 30.96. So in this case, we go minus 180 degrees. So when you have those two cases, if you get a positive, you subtract 180 degrees. If you get a negative, you add 180 degrees. But make sure that you got your angle right in the corrected quadrant, the quadrant that you were expecting your calculation to be. Okay, now let's move on to the next example here. In this example, we need to uh, find V naught t. So we need it in time domain, right? And it's given to me in time domain, but we have learned that the first thing we do is to transform it to the frequency domain. So in this case, what I will be getting, let me calculate first the impedances. So the impedance for the capacitor is going to be minus j 1 over omega c, and this is minus j 1 over omega is given to me as 4, and c as 10 millifarad. So z c in this case is, so we have minus j25. Always keep in mind that the impedance for the capacitor will always have to be negative reactance. It has to be negative reactance. For the inductor, it is j omega L, j omega 4 times 5, j 20 ohm. Right? So this is the impedances. And now I can redraw the circuit. And don't forget that this source, since it's a positive cosine, so things are right. Let me call this one Vs. So here, for example, I can say that this is Vst. So Vs capital is 20 minus 15 degrees. So now if I am to redraw the circuit again, okay, V naught, V capital, of course, naught, is here, in this case, the voltage across the inductor, which is also the same voltage across the capacitor, right? Because both of them are in parallel. So how do we calculate it? You can calculate it by, first, you can find the equivalent impedance for this capacitor and this inductor, and then use the voltage division. So here, if you say that This one is Z1. Then what you have is Z1 equals to. Now you look at them as impedances in parallel. You don't care. It's a capacitor. You are not finding the equivalent. You're finding the equivalent impedance. So you have this impedance minus J25 and another impedance J20 that is in parallel. So the total would be minus J25 times J20 divided by the summation, which is minus J25 plus J20. And in this case, Z1 becomes now J times J is minus. So you have here 20 times 25, 500. Now minus J5, right? Or the 5 cancel, and this minus J, when it goes up, becomes positive J. So this one now becomes Z1 equals to 100 or J100. J100 ohm. So in order to find the voltage V0, we said we need to use the voltage division. So this one is J100. What I can do here, I can say that I have V0. If I am to write, I can put this J100, which is equivalent to an inductor, right? So this one is 120.
Sir,
Yes,
why is it equivalent to an inductor? Because that has the higher value.
yes, because the value here is a J100, and this one is equivalent to a J omega L, right? If that was a negative reactance, then it is equivalent to a capacitance. So indeed, at this frequency, remember, this is those. Always keep in mind that those components, capacitors, inductors, are frequency dependent. Right at this frequency, which is omega equals to 4 radians per second, the equivalent impedance is equivalent to an inductive load. If you change the frequency, things may change. You may end up at one frequency that this impedance is different. Okay, so here we have 60, and now I need to find V naught, and V naught here is indeed a voltage division. 20 minus 15 degrees J100 over 60 plus J100, right? So I can simplify further. If I divide both by 10, I can get rid, or let me say both by here. Yeah, okay. So V naught becomes 20 minus 15. Remember this J100 here means 190, right? Divided by 60 plus J100. If I divide by 10 both, what do I get? Divide by 10, V naught equals to, let me first, this is 2000 before I divide by 10, 90 minus 15, which is 75 degrees, divide by 60 plus j 100, divide by 10, V naught is 275, 60 plus j 10. Now what I need to do, I need to transform this one into a polar, from rectangular to polar, which is 275 divided by 6 squared plus 10 squared, tan inverse 10 over 6. So it is in the first quadrant. Both are positive. V naught equals to 275 divided by 11.66, tan inverse 10 over 6, 59 degrees. So V naught is 75 minus 59, 15.96 degrees. 200 divided by 11.66, 17.15. This is false. Now, if I want to go to the time domain, I have the omega. Omega is 4. So here I have V naught T equals 2. This amplitude 17.15. I'll keep the same sinusoidal, which is the cosine, and then cosine 4t, and then comes my phase angle here plus 15.96 degrees volts. So this is my V naught t as a time domain function. Is this clear? Any question about that? You have the solution here as well. Any question?
Sure, can you go back and reconvert to the time domain?
Where?
I can't see how you write it in the time domain.
I have the magnitude, Matthias. 17.15. And I have the phase angle as well. So let me make this one different colors. So this phasor has a magnitude and has a phase angle.
So it'd be 17.15 cosine, what was it, 4t minus 15.96?
So the cosine 4t, this is not going to change. The cosine and the 4t are not going to change. Those are not going to change. I just need to put the magnitude in front of the sinusoidal function and update my phase angle. That's it. This is the the feature of using the phasors, where you basically take the magnitude and you take the phase angle to simplify your calculations. Why are you expecting it to be minus 15.96? Look at this rectangular number. When we found it, just a second, let me make sure. This was when we transformed this 6 plus j10 into polar. What did we get? We got 11.66 with a phase angle of 59, right? Then V naught is, you divide the magnitude and you subtract 75 minus 59. So the magnitudes, you divide the magnitude. However, the phase angle in the denominator will be subtracted from the phase angle in the numerator. Is this clear now? Okay. So let's move on to the next example. So here we have a capacitor, an inductor, a series resonator actually. We need to find the value, what value of uh, of the frequency, what value of omega, what value of omega will cause the force response V naught to be zero. So we know that the V naught is zero when the impedance is zero, right? So in this case, let's find the impedance of the capacitor and the impedance of the inductor. So we have here ZC is minus J 1 over omega C, or ZC is minus J 1 over, we don't know omega, but we know C, which is 5 milli, right? So this is ZC is minus J, then 10 to the power minus 3 goes up, becomes 1,000 divided by omega times 5, right? Or ZC is minus J 200 over omega. Oh, so we don't know the omega. We need to find the value of the omega that makes V naught zero. And for V naught to be zero, the impedance has to be zero. So let's first find the impedances for the inductor and the capacitor. For the inductor is J omega L as J omega times L is 20 millihenry, 10 to the power minus 3, right? Oh, so for V naught to be 0, this impedance, let me call this one Z naught. For V naught to be 0, the impedance Z naught should be 0. And I know that Z naught indeed is the summation of both impedances, ZC plus ZL, or Z naught equals to J omega times 20 to the power minus 3 minus J 200 over omega, right? I need to find omega when Z naught is 0. So in this case, I have J omega 20 minus J 200 over omega equals to 0, right? So J omega 20 power minus 3 equals to J 200 over omega. Now take omega, multiply by omega both sides. What do you get? You get, and of course J is going to cancel. You get omega squared times 20 power minus 3 equals to 200, right? Or omega squared is 200 as 200 divided by 20 omega squared is then omega is 100 radians per second. So basically, this is we've taken you step by step to find the resonance frequency actually, where you know that the resonance frequency omega is 1 over square root of also LC, right? So this is how you can find the resonance frequency, which is basically of what we have done here. If you go back to 5 milli times 20 milli, take the square root, and then take the inverse, you get 100 radians per second. So basically, this is what Q, and to calculate the resonance frequency of this resonator, that is a series resonator. Okay, so that's the concept behind the resonance and the series resonators here, as when the total impedance for those capacitors and inductors, this capacitor and this inductor are connected in series, I get a resonance, which is basically would be here the smallest impedance I have when the impedance of the inductor and the impedance of the capacitors cancel each other right at that frequency. Any question about this example?
Sure, this is the resonant frequency.
This is the resonance frequency. That's correct. So at this resonance frequency, and this is the angular one, right? If you want to calculate the f, would be 1 over 2 pi. Let's see, right? Because we know that omega equals to 2 pi f. Okay.
Okay.
Yes.
So at the resonant frequency, that's basically when you get no impedance except DC resistance.
Yes. You all what you have is the real resistance. There are no reactances. Okay, so let's move on to this example. So we only have two more lectures left. One of them is for the quiz number 3, and the last one, I believe, is on August 5th. So, oh, we have, no, we have two more actually. August 3rd and August 5th. We can use those ones for solving questions, as review lectures, solve more examples for you. Okay, so here in this example, we need to find the input impedance for that circuit. Yes. Yeah. Okay, so we need to find the input impedance for this circuit that has the dependent source, as you can see here. And in this case, we cannot calculate the impedance directly. We have to hook up a source to the input of the circuit and calculate, for example, the withdrawn current for this known voltage. So in order to do so, the frequency is given to me as 10 kiloradians per second. What we should do is the following. Because we have dependent source, we cannot calculate the impedance directly. So what we do is we hook up a source. But while we are doing this, we need not to forget to go to the frequency domain. So here we have 50 ohm, and this one now is phasor V, and this is ZL, and this is ZC, and we need here to hook up a source and calculate the withdrawn current. So ZL as J omega L, or omega as 10 L as 2. So ZL as J20 ohm, and ZC is minus J 1 over omega C 1 micro 10 to the power minus 3. Total goes up, becomes 1000 divided by 100 minus J divided by 10 minus J 100 ohm. So this one is minus J 100 ohm, and this one is J 20 ohm. We need to calculate the current. So in this case, if we take KVL, we can say minus 1 plus 50I. Let me add all those impedances all together. What I can say that 50 plus J20 minus J100, all of them are times I, plus 2V equals 0, right? Now this V is the voltage across the 50, so V equals to 50 times I. So if you take this one and substitute here, take this minus 1 to the other side, what do we have? What do we get? We get 50 plus J20 minus J100 I plus 2 times 50 times I equals to 1, right? Or take I outside, so what do we have? We have 50, I have minus J80, 2 times 50 is 100, is also inside, I equals to 1, right? Then I is 1 divided by 150 minus J80. So you need to transform this rectangular form into polar. 1 divided by 150 squared plus, I'm keeping the minus intentionally, so you know where did it go. Tan inverse of minus 80 divided by 150. Tan inverse of minus 80 divided by 150, which is the fourth quadrant. So the angle here is minus 28.07 degrees, or the current is 0.005928.07 degrees, or
So where did you get 170?
170. Yeah.
Where did you get that number?
Square root of 150 squared plus 80 squared.
I got 126.9.
Okay. I'm getting 170. So how do you calculate it? 150 square root of 150 squared plus 80 squared. Okay, so we got the current. This is the current. Now, what is the impedance? Z Thevenin is the voltage that we hooked up to the source divided by the current we got. Right? And this is going to be, guess what? Okay, yeah. So this is why I intentionally kept the minus there to show you that the minus is going to be disappear because it would be squared. So regardless, negative numbers, positive numbers, the magnitude is not going to change. Thank you, Liam, for looking into it. Okay, so this is how we calculate the impedance.
resistor, where'd you get the 1 volt?
Okay, so the 1 volt is the voltage that I have hooked up. And don't forget that since here I'm dealing with AC steady state analysis, this voltage source that I hooked up to that circuit has to be phasor as well. So it is one with a phase angle of 0, right? So this is the voltage that I hooked up to my circuit in order to calculate with the drawn current. So let me make this in different color. Exactly the same way we used to do for finding the R Thevenin for circuits that had dependent sources. Since this circuit is impedances, then it is not an R Thevenin, it is a Z Thevenin. So I hooked
We
up
include
this.
the angle with the Thevenin impedance.
Yeah, yeah, this is the Z Thevenin. It has an angle because the impedance here is not real. The impedance is made of a real and a reactance. So it is resistive and reactance, right? You have an inductor, you have a capacitor. Those are frequency dependent components. So definitely they will be having a net reactance. This net reactance is going to contribute into the Z Thevenin, which is the same concept of the Z Thevenin, right? Any questions? Any other questions? Okay, so the solution is given to you here. You can. So the last example, which basically I don't think we will be having time to finish it in 9 minutes. So we'll keep this one. I'll let you try solving this example on your own, which is basically exactly what the same thing of what we have done. You need to find the Thevenin equivalent circuit. So this is A and B. Find the Thevenin equivalent circuit for this circuit. Remember, this circuit has dependent and independent sources. So you have two options. Either find the V open circuit, I short circuit, and then Z Thevenin as V open circuit divided by I short circuit, and both are phasors, right? So this is one approach. Or you can switch off the independent sources and hook up a source at the output and find the withdrawn current. Exactly the same of what we have done in the previous example. Both are going to give you the Z Thevenin. Okay. Any question before we conclude today's session? No questions? Thank you so much for coming, and I hope you have a good day. And good luck on Thursday's, our last quiz on Thursday, quiz number 3. Thank you so much and have a good day.